Hey folks, Luke here again. I hope you've gotten through the last week safely and staying at home. So this week we're going to just go over some introduction to how you plot population growth in various ways, exponential and logistic. This presentation will just focus on the exponential, and then I'll do a separate one for logistic growth. We're going to do all this on Excel spreadsheets. I assume you guys are fairly familiar with Excel, and it turns out it's a great way to plot population growth using the models that we're going to be talking about. So we've got two things for you to look at in the lab zip file. One is this overview of population growth, and just kind of gives you the equations that we've already presented in lecture, and then focuses on a couple of equations that you need for what we're doing. One will be the intrinsic growth rate. We're going to follow this example here where we're using 1 plus r as a surrogate for lambda and just multiplying that times n sub t. And this, of course, is just the classic exponential growth equation. And we're going to look at this both deterministically and can also run some stochastic models. So let's just take a look at the template spreadsheet that I've put together for you. So this will just help you get started. You could do this on your own from scratch. That'd be great, but I know that we're kind of limited. I don't have the ability to be there with you to step through all of this. So hopefully this will get you started and still get you the important concepts that I really want you to get out of this lab. Okay. So up here is our exponential growth equation that we're going to use, and you can see from the first questions in the lab homework that basically we want you to produce some deterministic exponential growth equations using R of 0.02, 0.04, 0.08, starting with an initial population size of 20. Okay, so it's fairly straightforward to input the exponential growth equation into Excel. In Excel, of course, all functions have to start with an equal sign, or anytime you're doing some sort of calculation in a cell, the first thing you do is type the equal sign. And in this case, we're going to just, following the equation, take 1 plus the value of r that we want to use for this particular model. So we're going to use 0.02. But a very important thing here that you have to do, or you're going to get really strange results, is you have to change this from what we call a relative reference to an absolute reference. In other words, we don't want the position that Excel looks at to get this number to change. We want it to stay constant as we copy this equation. And the way we do that is we simply put a $ in front of the column, in this case B, and a $ in front of the row, in this case 13, in that equation, such that Excel is always going to look to that particular cell to find little r. Okay. Now for the next number we're going to use in the equation, which is n sub t, we simply go back and use the value of n in the previous time step. Okay. And this we do want to be a relative reference. So we're going to leave this as B17 and not put any $ in it. And we do that, and we get a value of 20.4. Now, it's always good to kind of look at these calculations and make sure it makes sense. So we're taking 20 and we're multiplying it times 1.02. So 20 times 1 is 20. 0.02 times 20 would be 0.4. So we get 20.4. Okay, that makes sense. So now neat thing about Excel, once you've done this once, you just copy it down. And bingo, you've got your exponential growth curve for an R of 0.02. Okay? And in case you didn't see how I did that, you just click on the cell you want to copy, come over here to the lower right hand corner until it says plus, and then click and drag down, and that will copy it all the way down. Okay, so now we want to do that, but instead of using 0.02, we want to use a growth rate of 0.04. So what I'm going to do is just copy this equation over, and if I double click on the equation, I'll see that one really nice feature of Excel is it highlights in different colors the cells that are being referred to in the equation. Okay, so here it's saying take 1 plus B13, which was correct for that first column, but now I want to use the value in C13, okay, for our growth rate, and it says take the value in the cell right above it, C17, and multiply it by that, and that's right. So we've got that right, and again that makes sense, 20.08. All right, and then we do the same thing. We just copy that down and let it go once we get to 50, and bingo, you see that this produces the curve for 0.02 and 0.04. Yeah, I set that up for you just to, again, make this simple so you can get through it. And then I'll let you figure out how you do that for the last column. Okay. The next thing we want you to do for the exponential growth equation. I should add one more thing. In one of the questions for the exponential growth, we ask you to plot the exponential growth on a logarithmic scale to see if in fact it is linear, because we all know that when you take a exponential equation and plot it against the log of y, that will give you a straight line. So very easy to do this in Excel. You just click on that y-axis and you'll see a rectangle that highlights the value in the y-axis. So you make sure you got that highlighted, and then it'll bring up this format axis area over here. It may not do that automatically in your case. Let's just start. If we click on it and nothing appears, then all you have to do is right click and click on format axis. Okay, and once you do that, you just click on logarithmic scale, and bingo, it changes the y-axis to logarithmic, and you can see right away that you've got two straight lines here. So we are plotting exponential growth. Okay, so let's now go on to how we add stochasticity. So basically what we're saying here now is rather than R staying constant on every time step, we want to let R vary. We're going to have a mean R because we want it to be, some long-term average growth of a certain amount, but we want it to vary from year to year because that reflects what we all know happens in real populations, right? You have cold snaps, you have drought years, wet years, all of that affects how quickly a population might grow. So in order to do that, we have to generate a random number for R that has a mean of a certain value and a standard deviation around that value. So again, it's pretty easy to do this in Excel. If we take a look at the overview, in here we give you somewhere just a quick description of the norm in norm.inv function that we're going to use for generating these random values. So you can see it's got the form norm.inv, so that's the function, parentheses rand. This is going to give us a random number, and this will be the mean from the normal distribution and the standard deviation from the normal distribution. And notice those are separated by comma. So we just have to replicate an equation like this in the Excel spreadsheet. So what we do is we just type our equal sign, and then we type rand.inv. Nope. Sorry, norm.inv. And then parentheses, for all functions have these parentheses. For the probability, we're going to use the random function. And we just put two parens, and that just tells Excel, just go ahead and go find your own random number. And then we do have to specify what the mean and the standard deviation are going to be. So I've got the mean up here. So we're going to use a growth rate of 0.05. And again, we want this to be an absolute reference. We don't want that the location of that cell to change as we copy it down. So a simple way to do this, and you won't be able to see what I'm doing, is you just hit the F4 key on Windows PCs, and it'll automatically add those two dollar signs, one in front of the column, one in front of the row. And then we want to specify the standard deviation, so we click on that value for SD that we have right below the mean. And again, I'm going to hit F4, and then parentheses to finish all that up, and bingo. And notice that even though we have a mean R of 0.05, for this first value of R, we get actually a negative value, 0.03, okay? And again, that's because what this function is doing is it's giving us a distribution of R values that overall have a mean of 0.05, but are allowed to vary above and below that value according to the normal distribution. So what I'll do now, I've got that the way I want it. So I just copy it down. And again, we're going to go to 50 values. And then, you're not going to be able to just look at this and say, oh yeah, those are all correct. So one thing that's always good when you're generating random numbers like this is just to check it out and say, okay, does this really make sense in terms of the average value that I'm calculating? So you might not have seen what I did there, but basically I just came over to the AutoSum function, clicked on the down arrow, clicked on average, and then it'll automatically say, hey, I probably want the average of all those numbers above us, which is what I want. Sometimes it's good to look and make sure. Sometimes it'll grab more values if you have a numeric value above the column, but it's got it right. And so I hit enter, and bingo, it tells me, yeah, the average, these are all over the place. Bunch of negatives, bunch of positives, but the average is about 0.05. Okay. The other kind of cool thing is if you hit F9, again, it'll grab a whole set of new random numbers and then take the average of them. So now we've got 0.4, 0.04, 0.03. So it's bouncing around 0.05. So that gives me confidence that I've got that right. So now we just put in an equation for exponential growth, and the same thing we did before. We say 1 plus, but now what we do is we grab a different value of R for each time step, and we tell it, go and look at that R value that we generated for the first time step, okay, and then add 1 to it, and then we multiply that times the last value of n. So in this case, in this equation, everything is a relative reference because we want R to change each time step, and of course we have to use the last value of n on each time step. So now we just copy that down, And bingo, we've got a stochastic exponential growth. And again, it's going to plot it for you here as you get both the n. Well, first you have to do the r value, and then it's plotting the values of n over time. Okay, and I'll let you figure this out for the next time step. Again, here we want to use the same value of r and standard deviation of r. So really you could just grab these two columns, copy them, paste it here, and that should give you the values that you want. Let me just do that. I want to make sure there's not something I'm forgetting that you have to change here. So it's always good, like I said, to check and make sure things are referring to the places they should. And yes, Excel remembers, okay, these are absolute references, so those are the mean and the standard deviations we want to use. Okay, and then for our values of n, we're saying take 1 plus the value of r that we randomly calculated in that previous time step times the value of n sub t in the previous time step. And so that all looks right. And notice that it gives you different curves because now it's a whole set of different r values. And you'll notice that every time you hit enter, what Excel does is recalculates all those random numbers. So these things are going to keep changing over time. And I think that's all you need to get this first part of the homework done. So good luck with it. I hope you can follow this.